This is the second section of Unit 4. All right, so now what we're going to do is learn how to draw orbital diagrams and electron configurations. What they are, okay, as you can read, the orbital diagram is a drawing of the different orbitals. We represent those with lines. Sometimes you'll also see them represented as circles or squares. In this PowerPoint, they're going to be represented as lines. And we're going to represent the electrons as arrows. So an orbital diagram is sort of a picture of where all the electrons are in the atom. Now, an electron configuration is actually a shorthand way of showing those same electrons, and what we're going to do is show how many electrons are in which subshell, which shell, etc. All right, so here are the rules for drawing orbital diagrams and electron configurations. An electron configuration, let's see, first of all, if you have electrons, they are going to always occupy the lowest energy orbital first. If that's filled, then it's going to go up to higher orbitals. So electrons will always go into the lowest energies first and then move up, and we're going to call that the building up principle, named after a scientist, Aufbau. So that's called the Aufbau or building up principle. We're always going to put electrons in the lowest energy level available and then add electrons in increasing energy levels. Now, each orbital can hold only 2 electrons. We said they have to have of opposite spin. This is called Pauli's exclusion principle. And then finally, if there are more orbitals, more than 2 orbitals with the same energy level. So for example, the p orbitals they come in threes. There's 3 p orbitals. They're all the same energy level. Or there's 5 d orbitals. What's going to happen is they're each going to fill halfway until that whole subshell is half filled, and then they'll go back and pair up, and you'll see that as we go along. And this is called Hund's rule. So keep these 3 rules in mind, and I'll come back and highlight them for you when they come up. All right, so energy of electrons. The energy will increase with increasing shell. So we already knew that. So the first shell is lower than the second shell, is lower than the third shell, is lower than the fourth shell. Now, we get into a little bit of a problem here. Oh, let me back up for a second. So subshells also increase as we go, S being the lowest, and then P is higher energy, D is higher energy, F is higher energy. But take a look at the picture to the right, and you'll start to see that they start to overlap a little bit. So even though the overall 4th energy level is higher than the 3rd energy level, notice that the 4s line actually comes down and is actually lower than the 3d line. And so this is important to remember, and there'll be ways to remember it as we go along. But if you look on the right, this will be the order of filling electrons. So remember, we said that the Aufbau or building up principle means that the electrons will start at the lowest energy level and they will continue building from there. And so if we kind of go in order of energy, 1s, then 2s, then 2p, then 3s, then 3p, then 4s will come before 3d, then 4p. And actually, it gets even more complicated the higher up you go. Here you can see on the bottom left, I've listed the order: 1s, 2s, 2p, 3s, 3p, 4s, then the 3d, 4p, 5s, then the 4d, then the 5p. You start to see that it gets complicated. One thing you can do is just kind of memorize this, or write it down on your index card. Or in a few minutes we'll see how it works. You'll see a way to remember it. Okay, so here's how it's going to work. we start with hydrogen. Just look at the center, the orbital diagram for now, and then we'll talk about the electron configuration in a minute. So remember that the off-bow principle says that we put the electrons in the lowest energy orbital available. So hydrogen has one electron. So where does that one electron go? Well, the lowest energy orbital is the 1s orbital. So we put that one electron in there, and that is actually the orbital diagram for hydrogen. Helium has 2 electrons, and remember that the electrons are the same as the number of protons, at least for right now. When we get into chapter 5, it might change, but for right now, electrons equal protons. So helium has 2 electrons. Now, the first one, as we just saw, should go into the 1s orbital, and since every orbital can hold 2 electrons, then the second electron will go in that orbital as well. Now, remember that the Pauli's exclusion principle, rule 2, says that we have to have them of opposite, electrons have to be of opposite spin, and so we put the arrows one up and one down in order to represent opposite spins. Now, it doesn't matter if you put the first one up and the second one down, or the first one down and the second one up, as long as they're opposite of each other. All right, so now if we go to element 3, lithium has 3 electrons. We put the first 2 in the 1s orbital. Now, the first shell is totally full, because remember that the first shell only has a 1s subshell, and a 1s subshell only has 1 orbital, so it only can hold 2 electrons. So the third electron cannot go in that orbital. It has to go into the next highest energy level, which is the 2s subshell and the 2s orbital. So remember that the second shell has a 2s orbital with 2s subshell with 1 orbital, and a 2p subshell with 3 orbitals. So, and s's are always a little bit lower than p's, and so that electron goes in the 2s subshell. Now, beryllium has 4 electrons, and so the fourth electron, as you can see there, goes in the 2s orbital, also opposite spin, and so we have 2 in the 1s orbital and 2 in the 2s orbital. Now, it doesn't go into the 2p's yet. It completes that 2s orbital because the p's are higher energy than the s's. So now when we go to boron with 5 electrons, we've got the 4 that we've already seen. The 5th electron now has to go into the 2p subshell. So we put it in the first box. It doesn't really matter which box or which line you put it on. Remember that there's 3 of them. Whenever you're doing orbital diagrams, if you're putting electrons into a particular subshell, you should put all the orbitals that belong to that subshell. So notice that for boron, I put the 2p subshell and I've drawn 3 lines, and so even though they're not full, I represent that there are 3 orbitals. All right, now when carbon comes along, notice that I put the next arrow in the second line, on the second line, rather than pairing up the first 2. This is rule 3, the Hund's rule, that says if you have orbitals of the same energy level, and all 3 of these p orbitals are the same energy level, then the electrons want to half fill the orbitals before they pair up. So that's why we put that second arrow on the second line rather than pairing up the first arrow. And then nitrogen, the 7th electron will go on the 3rd line, so you can see that. All right, now we're going to continue on in just a minute, but let's look at the electron configuration. So the orbital diagram shows the lines and arrows, and the electron configuration just as a shorthand method of indicating it. And so the way that you do it is you just put what the orbital is, or what the subshell is actually, and how many electrons are in that subshell. So 1s1 for hydrogen just means that there's 1 electron in the 1s subshell. 1s2 means there's 2 electrons in the 1s subshell. Lithium has the electron configuration 1s2, 2s1 because it has 2 in the 1s subshell and 1 in the 2s subshell. Beryllium 1s2, 2s2, and then you can see that boron has 1s2, 2s2, 2p1. carbon 1s2, 2s2, 2p2, and then nitrogen 1s2, 2s2, 2p3. And then we're going to continue on in just a minute. All right, so now oxygen with the 8th electron, because the 3s subshell is higher than the 2p, now we're going to fill up the 2p subshell before we go on. So now that they're half filled with one in each orbital, the next electron will have to go and pair it. So oxygen, we put number 8 pairing up with the first line, number 9 for fluorine pairing up with the second line, and then neon pairing up with the third one. So neon has 10 electrons, and you can see the electron configuration for neon, 1s2, 2s2, 2p6. So because the p subshell can hold up to 6 electrons, we just keep adding one in our electron configuration until we get up to 6. Now sodium has 11 electrons, so what do we do with the next one? We're going to have to go to the next highest level, which is the 3s subshell. The 3s subshell has one orbital, and so we put 1 electron in there. And then magnesium has 12 electrons, so we pair it up because because remember that S's only have one orbital and can only hold 2 electrons. So then if we keep going, and I haven't drawn the orbital diagrams, but I've drawn your electron configurations. For aluminum, 3s2, 3p1, phosphorus, 3p, go across, so aluminum, and then silicon has 3p2, and then phosphorus 3p3, sulfur 3p4, chlorine 3p5, argon 3p6, and then what do we have to do next? We have to go to the 4th level. So potassium 4s1 and then calcium 4s2. This is why it's really helpful to learn that order that was on a few slides ago. And again, in just a few minutes, we're going to be able to understand how you can do this by looking at your periodic table. All right, so I just said that. Remember that the order of filling electrons looks straightforward at first, but then it gets off a little bit. So I gave you, on a few slides ago, I gave you the order of filling: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 5s, 4p, etc. Now, one way that you can remember the order is just to write it all down and put it on your index card, or memorize it, or you can use this little mnemonic device here. You can see on the lower right hand corner, if you line up the S's in the first column and then the P's in the second column, and then you draw diagonal arrows, you can follow the order. So 1s, and then 2s, and then 2p, 3s, and then 3p, 4s, and then 3d, 4p, 5s, 4d, 5p, 6s, so forth. We're actually not going to go that high on the ones that we do. I believe we're only going to go up to 5s, so you don't really have to worry much beyond that. Maybe actually maybe the 5p would be the highest that we're going to go. But like I said, we're going to learn an easier way in a few slides. And then also just keep in mind the maximum number for each electron. S subshells can hold 2, P's hold 6, D's hold 10, and F's hold 14. And then also keep in mind that if you're on a P subshell and there's 3 orbitals, they half fill and then they go back and pair up only after each one has 1 in it. Then they go back and pair up. And that's Hund's rule. Okay, so let's look at some examples. Write the orbital diagram and electron configuration of phosphorus. So, first thing we want to do is look up and see that phosphorus has 15 electrons. So, I'm going to start. Actually, you can add the lines as you go along. I've put the lines here. You can label them. So we've got our 1s, 2s. If you want to, you can just put the 1s, put those electrons in, then go to the next one, 2s, and then the 2p, and so forth as you fill them. You don't have to put them there until you fill them, because you don't need them all unless you're going to put electrons in them. All right, now 15, let's start counting. All right, 1, 2, that fills up the 1s electron, or 1s orbital. 3, the next one fills up the 2s orbital, so 4. Now, the 2p's, remember, are the same energy level, so 5, 6, 7. They're each going to half fill their each orbital until they're all until each orbital is half filled. So then 8, 9, 10, and now the 2p subshell is filled. 11. Now the 3s only has one orbital, so we're going to fill that one up, 12. And then again, the 3p's will also do the same thing that the 2p's did. So now we have 12 electrons, 13, 14, 15. And so that's what the phosphorus orbital diagram looks like. So what is the electron configuration? Well, there's 2 in the 1s, so 1s2, 2s2, 2p6, 3s2, 3p3. So there's the electron configuration for phosphorus. All right, how can the electron configuration of zinc be assigned? Well, I'm going to go through it step by step. So I think once you get used to it, you could go ahead and just write it out without figuring it out like this. But I'm going to go step by step so you can see where the numbers are coming from. So first of all, you need to look up zinc. Zinc has 30 electrons. Now, the first shell will hold 2 electrons. So now we have 28 left. Okay, the second shell holds a total of 8 electrons, 2s2, 2p6. So that leaves 20 left. The third shell starts with the 3s2, 3p6, so that's 8 more. So if we subtract that, that leaves 12 left. Now remember that before the 3d's come in, the 4s's come in. So the 4s's fill, so that's 2 more, 4s2. That leaves 10 more electrons. Now the 3d's can hold 10 electrons, so all the rest will go into the 3D or subshell, so 3D10. If I happen to have 11 more, then I'd have to go on up to the next shell, the next level, which would be the 4Ps. So, well, because all 10. Now, if there only happen to be 9 left, then it would be 3D9. Okay, so here's the electron configuration for zinc. All right, let's write the electron configuration for chlorine, iron, and element 36. So first of all, chlorine has 17 electrons. Here we go. 1s2, 2s2, 2p6, 3s2, 3p5. So if you add the total, you should find that you have 17 electrons. So again, you just keep adding them. If you want to draw the orbital diagram out first, that's fine. Remember that the 1s orbital holds 2, the 2s subshell holds 2 with 1 orbital, the 2p subshell holds 6, 3s holds 2, and then the 3p can hold the rest of them up to 6. If we had more than that, we'd have to keep going on. All right, now iron is element 26. So what we're going to do is continue on. So it'll start with the same thing, and then we'll have 3p6, which would be 18 electrons, and now we have to go into the 4s electrons, and there'll be 2 more, and then we go into the d electrons. So here you see that we have 2 in the 1s, 2 in the 2s, 6 in the 2p, 2 in the 3s, and then 6 in the 3p. Now we have 8 more electrons, so 2 more go in the 4s. 4s2, and then the rest go into 3d. Remember, the 3d can hold up to 10. Okay, finally, let's look at element 36, which is krypton, and this is going to give us a good, nice, long one. So far, iron has 26, and so we're going to keep going. So, 2 in the 1s, 2 in the 2s, 6 in the 2p. So the second shell is full with 8 electrons. Then 3s2, 3p6, Now remember the 4s's come next, and there's 2 in there. Now we can totally fill the 3d with 10 electrons, and that brings us up to 30. And then we need 6 more, and the p's can hold 6, and so 4p6. And notice we've gone in the correct order. All right, now for an atom containing 33 electrons, identify the incompletely filled subshell and show the paired and or unpaired electrons in this subshell using up and down arrows. Okay, so let's go through this step by step. All right, so let's do a practice together. For an atom containing 34 electrons, identify the incompletely filled subshell and show the paired and or unpaired electrons in this subshell using up and down arrows. All right, so let's work through this one. Shell 1 has 2 electrons. Shell 2 has 8 electrons, 2s2, 2p6, so that's a total of 10 electrons now that we've accounted for. 3s and 3p have 8 more, 3s2, 3p6. So that's a total of 18 electrons. Then the next subshell is the 4s orbital with 2 more electrons. So now we've accounted for 20 electrons. The next one will be the 3d, which can hold 10 more. So now we have a total of 30 electrons accounted for. What comes after 3d? Then it comes 4p subshell, so the last 4 electrons would go in the 4p subshell. Now, how will they be arranged in that subshell? Well, here, let's first look at what the electron configuration is. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. All right, how would they be arranged in that 4p subshell? Well, notice that there's 3 orbitals within the 4p subshell. So first we'll fill each one up halfway. So if we have to put 4 electrons in there, we'll have 1, 2, 3. And then we have to add 1 more to the first line. Actually, it doesn't really matter which one you put it in, but just start back at the first one. So this gives us 2 unpaired electrons in the 4p subshell and 2 paired electrons. All right, now we're ready to answer some of these questions. Why is it that elements in the same column have similar properties? And how is this related to its electron configuration? And so on the next few slides, we're going to show, first of all, you may have already noticed this, but we're going to kind of put it together. There's different areas of the periodic table that you'll see the S section, the P section, etc. So we're going to divide the periodic table into blocks according to subshells. All right, so this is a good picture. So notice that the first 2 columns we call the S block, and they're pink in this periodic table. And remember, S's always have 1 orbital, so S's can always hold 2 electrons, and so that's why we have 2 columns for the S block. Notice that helium has that funny little, we'll talk about this later, but helium is over there in column 18, and so it's actually an S electron. All right, then jump on over to the P block. The P block, which is 13 through 18, or 3A through 8A, if you use the A designation, those are the p electrons. Now remember that the p subshell has 3 orbitals for a total of 6 electrons, and so we have 6 columns to represent the p orbitals. Notice that the S's and the P's have the same period number as the period that they're on. So notice the 1S's are on the first shell. The second line, the second period has the 2S's and the 2P's. The third period has the 3S's and the 3P's. The fourth period has 4S's and 4P's, and so on. Now, the blue boxes is the D block. Now remember that the D subshell has 5 orbitals for a total of 10 electrons. And so you can see that those are actually columns 3 through 12, or if you use they're all the B columns if you use the Roman numeral or the AB section. So there are 10 boxes for the D block. Because there's 10 electrons in every subshell. And notice that this is where we start to get off a little bit. Notice that the D's are one number behind whatever row they're in. So the 3 D's are in the 4th period, and the 4 D's are in the 5th period. So they're one behind. And then finally, the F block are those 2 columns, those 2 rows on the lower right hand part of the periodic table, and F subshells have 7 orbitals for a total of 14 electrons, and so you'll see there are 14 boxes. So it kind of pulls it all together. Now notice, you probably can't see that here, but the 4 F's actually come after the 6 S's, so they're on the 6th row, and the 5 F's actually come after the 7 S's, and so they're on the 7th row. I think the next slide will show us how it's laid out, or the next slide, I guess. So again, notice the S block. Then groups 3A through 8A are called the P block elements. Or 13 through 18 if you use that numbering system. Together, the S block and the P block are called the main group elements. And then the elements that are in group 1B through 8B, or rows 3 through 12, are called the D block elements. Sometimes we call those the transition metals. And then finally, the 2 rows that are detached are called the F block elements, and sometimes we call those the inner transition metals. And like I said, notice that the D block is one number below the row number. So it's the D block in row 4 is actually the 3 Ds, and then the F block is 2 behind. So we'll see on the next slide how it's kind of laid out. So here it shows us the F's put in place. So notice now, if you start following the periodic table, notice that the first 2 electrons are in the 1s, and then the next 2 are in the 2s, and then if you keep following along, you come to the 2p's, then you come to the 3s's, and then you come to the 3p's, then you come to the 4s's, but notice that the next thing after the 4s's are the 3d's, then the 4p's, then the 5s's. I'm going left to right. I keep filling and I keep going down to the next row left to right. So the 5s's, and then after the 5s's come the 4d's, then the 5p's, then the 6s's, and then see that the 4f's come in there. 4f's, which are elements 57 through 70, and then the 5d's, 6p's, 7s's, then the 5f's, and then the 6d's. So like I said earlier, you don't necessarily have to memorize this, because if you have a periodic table, you can follow along. And that's why I particularly like the Web Elements periodic table, because it shows those elements 57 through 70. It shows them on the periodic table, so you know that they come in there. You don't get confused. Okay, so you might want to go back and look at slides 26 and 28 and see if you can get the same answers using the periodic table. For example, chlorine, if you see, we went through the orbital diagram and everything, but if you just follow along with the periodic table, you see it's 1s2, 2s2, 2p6, 3s2, and then 3p5. Chlorine ends with 5, so you just have to count the last one. Iron would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. There's 6 of them in the 3ds. And then krypton goes all the way to 4p6. The one on slide 28, which is element 34, ends up with 4p4. So you should hopefully, you should be able to get that. All right, let's identify the elements that have the following configuration. That first one should be ending with 4p1. That would be gallium. All right, and then 4p, let's see. All right, and then the next one, if it ends with 3d8, if you look in the 3ds, that'd be element 21, 22, 23, 24, 25, 26, 27, 28. That should be element nickel. All right, so that's the end of the second session, and we'll do one more to finish up the rest of Unit 4.